I could take it over from here. Yeah, thank you. Yeah. Thank you.
Cool. I think I made this too big, though, by the way. So.
No, I think that's good. Yeah. I'm on? Yeah, okay, I'm on. Great. Hey, everybody. Before we start with our usual warm-up, I'm going to do a little recap of Chinese remainder theorem because we went through that a little bit quick last time. And we only did it for 2 things. So I just want to have a quick look at what happens when we have more than 2 things. That is 3 things here. So I'm going to write a few things up here. And then we're going to analyze it instead of trying to create it ourselves because we have a lot to get to today, per usual. So what I'm going to do here is, so the Chinese remainder theorem is always a system of linear equations over different moduli. And it's kind of a magic trick that we can make any sense of that we can solve a bunch of systems of linear equations when we have different moduli all at once. And we went over one of them last time. That is, we went over 2 equations. And if you look at the notes, it gets a little bit more confusing when we look at more than 2 equations. So I just want to give you a quick look at this so that we don't completely confuse ourselves when we get to the notes. And I said the Chinese remainder theorem is kind of a magic trick last time, and it kind of is. But also, it's a little bit more than a magic trick. It is a switch that we're creating with algebra. It's a pretty wild thing. We're kind of creating, radio buttons, those old school radio buttons where you press in and all the others pop out. You press one in, all the others pop out, and you could do that to any one of them. That's kind of what we're creating with algebra. So we're almost creating this machine with algebra. It's pretty wild. So how do you create a switch with just using algebra tools? We did it kind of last time for 2, so let's look at 3. What we're wanting to do is we want a single x that satisfies all 3 of these equations. We want it to be 4 when it's mod 7, we want it to be 3 when it's mod 5, and we want it to be 1 when it's mod 3. So we just kind of set up, we want 4, we want 3, and we want 1. And we want to be able to switch between those as we switch moduli. And it's pretty wild that we can do that. So let's just take a look real quick. Let's look at the middle one. Let's say we want, when we do mod 5, we get 3. So let's look at this equation, mod 5. What happens to this right here, just this term, mod 5? 0. 5's right there. If we mod 5, this 5 becomes 0 and cancels out this entire term. Over here, if we do mod 3, or if we're still doing mod 5, what happens to this term? Also 0. There's a 5 right there. Cancels that out. Well, this middle term, here's a 5 right here, so how come this doesn't get canceled out as well? We did this clever little thing where we divide by 5 as well, so it kind of punches a hole out right here for 5. So when we mod by 5, this doesn't just go away. So we're kind of doing this radio button trick. So when we mod by 5, this goes away, and this stays here. And now we have 7 times 3, which is 21, which is a bummer. We wanted to do mod 5. We wanted 3 left. But now we have 3 times 21. Not what we wanted. So the trick here is we can just multiply it by its inverse. And a little bit of new notation, so we're not writing a whole bunch. But we're going to just say that this is basically 21. What this notation is saying is 7 times 3, 21, inverse mod 5. So whatever that number is, we're just going to slap that in there. So now when we do mod 5, these go away. And what's left is 3 times 21 times 21's inverse with respect to mod 5. So mod 5, 21 times its inverse, this just becomes 1. So 3 is left. And we can kind of do this to any of them. So if we do mod 7, what happens to this term? 0. There's a 7. This also becomes 0 because there's a 7 right there. But this doesn't because we cleverly canceled out our 7s. So what's left is 4 times 15 times 15 inverse mod 7. So if I do mod 7, 0, 0, 4 times 1. So all we did was and we can do the same thing for mod 3. Again, we have this, we cancel out the 3's so that 3 makes this goes away, 3 makes this go away, mod 3, but this remains. And what this trick allows us to do is it creates this radio button with just using algebra. So in this way, if we look at mod 7, all we're left with is 4. If we look at mod 5, all we're left with is 3. And if we look at mod 3, all we're left with is 1. So whatever this x is, once we do all of our calculations, it will satisfy all 3 of these equations. That's the trick. So we can just kind of finish this off and write it. That's 4 times 15. And 15 inverse mod 7. Well, first off, what's 15 mod 7? Just 1. 7 goes into 15 2 times with the remainder of 1. So the inverse of 1 is 1. So that just comes out to be easy. Then we get 3 times 21 times, OK, now what's 21 inverse mod 5? First off, what's 21 mod 5? 1. So 1 inverse. So again, this one becomes easy as well. 1 is its own inverse. And then lastly, we have 1 times 35. And this one's not as easy. 35 mod 3. Show me on your fingers. 2, yeah. 3 goes into 35 11 times to get 33. 2 left over to get 35. And then the question is, OK, what's 2 inverse mod 3? That is 2, because 2 times 2 is 4. Mod 3 is 1. So 2 is its own inverse. 2 times 2 is 1. Again, we're still getting used to that weirdness. 2 times 2 is 1. In modular arithmetic, let me write that a little bigger. So then we could just write this all out. 4 times 15 is 60, plus 62, plus 70. Sorry, what was that? 63, thank you. Great, keeping me honest. And then all that together gets us 193. And if you checked, 193 would satisfy all 3 of those equations. What's that? Sorry, what's that?
Sorry, I said there was no guess and check essentially when you do it in this computational method.
There's no guess and check, sorry?
I think, yeah, that's what I meant.
OK. Yeah, so this isn't so much of a guess. We just kind of calculated it out, and we can check that it does satisfy those things. One thing we want to do from here, though, is 193 does satisfy it, but there are more things that satisfy it. In fact, there's infinitely many, and we'll see what those are real quick. We can mod this by the common factors. 7 times 5 times 3. Oh, I'm running out of room there. But that is, what is that again? 105, thank you. That's equal to 105. So the set of solutions, this is congruent to 88, if we're looking mod 105. And really the thing to check is that all the solutions that we have are going to look like 105K plus 88. Those are all possible solutions. So we have a lot to get to, so we won't spend too much time on this. But if you looked at 88, that will satisfy all 3 equations. And anytime we get 105, this will become 0 mod all of these, because each one of them divides it. 7 divides 105, so that'll become 0. 5 divides 105, that becomes 0. 3 divides 105, that becomes 0. So here's all possible solutions to these sets of 3 equations. The smallest positive one is 88. So I just wanted to give you a quick look at that because you have a homework problem like it, and we hadn't seen it for 3. And really, I do want to impress on you that one pretty wild thing we're doing is we are kind of creating a machine out of algebra. We're at the point in the class where we're going to start seeing more and more applications of all the math we've been learning. We've been learning how to prove things. We've been learning how to do modular arithmetic and all this sort of stuff. Now we're going to start constructing things out of it and showing all the different tools we can build out of that. Right. So Yeah, any questions on this before we kind of move into all the stuff we have to get through today? Great. So yeah, this is basically radio buttons created directly out of algebra. So like usual, we're going to start with a warm-up. So maybe you had a chance to look at this for now. Consider Z6. We haven't been calling it that, but if we're looking mod 6, these are the only numbers that really exist. Of course, there's a bunch of different numbers, but like all the things that have a remainder of 5 might as well be 5. All the things that are multiples of 6 might as well be 0. We can kind of talk about Z6 as the clock of arithmetic. We can just add and multiply and whatever we want to these mod 6. And how many elements of Z6 have multiplicative inverses? It's a fair question. You know, not all of them have multiplicative inverses, but how many? So first off, what does it take for an element to have a multiplicative inverse? Okay, I'm hearing GCD of 1. Yeah? Okay. So x has multiplicative inverse. And we've seen this a few times now, but you know, it's fast, so we have to kind of keep seeing it. X has a multiplicative inverse, you know, mod 6, if and only if GCD of x and 6 is equal to 1. Right. So we can just write them out, right? We have 0, 1, 2, 3, 4, 5. Okay. Does 0 have a GCD of 1 with 6? No, what's the GCD of 0 and 6? 6, yep. So that one's out of the cards. 1. What about 1? GCD of 6 and 1. 1, great. 2? 2, okay, so that's out of the cards. 3? No, 3 is out of the cards. 4? Yep. So all we have is 1 and 5. So the answer to this is 2. This is small enough where we can just look at them. But looking at them may not always be the easiest. I'm going to erase this now. If we wanted to do it for 35, that's not so easy. Right? There's a lot we'd have to list out, and we'd have to look at them. Yeah, we'd really have to kind of look at them for a moment. And I don't know, you know, if you've seen it before, then you know how to do this. If you haven't, it's not so obvious. So let's look at 6 again, a little bit more structured. So let's say we have a 2 by 3 grid. And here's 1, 2, 3, 4, 5, 6. We know that. Why do we have 2 by 3? Well, because 6 is equal to 2 times 3. Right? So we know that anything that shares a multiple with 6 is out of the question. So how many multiples of 3 are there is a problem. We have 2 multiples of 3 there. So those can't be, those are things that can't have multiplicative inverses. So already we started with 6 elements, and we say, well, 2 of those don't have a G. 2 of those share a factor with 6. 3 and 6 share a factor. We didn't get all of them, though. We missed some. We missed some that aren't relatively prime, aren't co-prime with 6. So we could look at this another way. We could look at it as a 2 by 3. 1, 2, 3, 4, 5, 6. And now we see more things that are not relatively prime, namely all the multiples of 2. Right? Here's 1, and here's 1. So there's another 3 that should be taken out. There's a problem here, though. First off, 6 minus 2 minus 3 is 1. So what happened here? Why did we not get the correct number? Yeah. We double counted 6, right? Let's use a different color. 6 is counted twice in here. So we need to add that back in. And that gives us 2. Okay. Yeah? Oh, good question. Great question. So I could, well, what is 6 mod 6? That's 0. So I could have written 0 instead of 6. The main point is we want to look at, first off, 2 times 3, how many multiples of 3 they're going to be, how many multiples of 2 they're going to be. We're seeing a multiple of 3 being 3 and a multiple of 3 being 6, which is same as 0, and same with this. So let's take a quick look and see if we can think about how many things have multiplicative inverses mod 35. Right. So now if we're looking at mod 35, let's draw it here. So let's say we have 5 by 7. We're going to have 1, 2, all the way to 5. And then we're going to have 6, 7, all the way to 2 times 5. And then we're just going to keep doing this until we get to 7 times 5. So here are all of our multiples of 5. Sorry, that should be 7. Thank you. Hearing some murmurs there. Yep. 5 by 7, so we're counting up to 7 here. 2 by 7, 7 by 7. Great. So here's all of our multiples of 7. How many of them are there? Just 5, right? We have a 5 by 7. So first off, we have our 35, and we can take out 5 of them. And now we could draw this again. Our 7 by 5. And we have across our rows 1, 2, all the way to 5. 6, 7, all the way to 2 times 5. And now I'm realizing this should not be 6 and 7. This should be 8 and 9. All right, let's make sure we're... And then we get 7 times 5 down here. So there are all of our multiples of 5. Right.
Isn't that corner 5 times 7?
Yes, it is. This was when I was still counting it wrong. Thank you very much. 5 times 7. Great. So we have 7 multiples of 5. So we should take those out as well. And again, we did something bad. We double counted. We have 7 times 5 and 5 times 7. Those are the same. So we have to add that back in. And nothing else is double counted because 7 and 5 don't share any factors. Yeah?
Wait, can you explain why you have to draw the rectangles to solve these problems? Why you have to draw 2? I'm kind of lost.
Yeah. So we don't have to do this. This is just a way to visualize it. It's a way to kind of keep track of and tabulate where we're getting common factors. 35, first off, we need to know that 35 is equal to 7 times 5 for this to even start to make sense. But we know there's only 2 factors. So if we draw a rectangle, it lets us see like, oh yeah, there's all the places where we get a factor of 7. Those need to be ruled out, right? Because for something to have a multiplicative inverse, it needs to be relatively prime to it. So this is just a way for us to tabulate and keep track of where the multiples of 7 are and where the multiples of 5 are, so that we can, again, we don't need to. It's just if I asked you this flat, that is how many things have multiplicative inverses, Z35? That may have been tricky to do. I'm not sure if people had the answer offhand, which is whatever this is, which is what? 35 minus 5 is 30, minus 7 is 23, plus 1 is 24? That good? Okay, great. So, yeah.
What do you do for if your modular space is not a product of primes, and if you have something like 40, then how would you draw a two-dimensional space?
Right. Great. So the question is, what if your thing isn't a product of primes? Then what? Well, to some degree, it's always a product of primes. But the question, I think, is, what if it's more than a product of just 2 primes? Then you need to get, you need to generalize this, and you need to think a bit harder. Right. We're just looking at this simple case to begin with, and just kind of reasoning through, well, the things that are a problem are things that have 5 in them and the things that have 7 in them. Like those are the things that will have a GCD other than 1. Because there's only 2 factors that can be a problem. There's only 2 things that can share. So this is just our way to find out where those are. Here's all of our factors of 7. There's 5 of them. And here's all of our things that have a factor of 5. There's 7 of them. I saw a hand? No? OK. OK. So, right. We have 5, and then we're double counting the 7 times 5 and the 5 times 7. Yeah?
Would it be easier to look at this like as a Venn diagram instead of like 2 rectangles?
We could. I don't know what that Venn diagram would look like offhand in a way that kind of makes it clear, like, oh, there's all the multiples of 7, there's all the multiples of 5. But drawing bad pictures and using high-powered reasoning about it, that's math. So if you have a better picture, absolutely, that is great. This is just a simple way for me to kind of look at it and be like, oh, OK, where are all the factors that are going to be a problem? And then suss them out like this. So if I asked a more general question, I'm going to erase. Yeah, I'll erase this. So if I ask a more general question now of what about n is equal to p times q for p and q prime, the question is, what about Zn mod n? How many multiplicative inverses does this have? And the reasoning goes the same, except it's more abstract. If we have this being p and that being q, we go all the way up to p, and then p plus 1 all the way up to 2p, all the way down to p times q, or q times p, however you want to write it. And then that's going to be q violations, that is q numbers that have a factor of p, which is a no-no because we need a factor of 1. Or, yeah, we need the GCD to be 1. So there's pq elements. We can already subtract q. And as we were arguing before, we can kind of look at it both ways, 2q all the way to pq. This is now q by p. Yeah, that's fine. So we need to subtract that other p. And the last thing we need to do, of course, is add that 1 back in because we double counted. The real thing to note here, or the reason why this makes it a little bit easier to see is, well, I'll just write it out. Those two are actually the same. If I FOIL these out, I get that. So the number of things relatively prime to n that is a product of 2 primes will be p minus 1 times q minus 1. And a nice way to see that is if we kind of write out these grids and like, oh, there's all the things that are sharing a factor they shouldn't, and there's all the other things that are sharing a factor they shouldn't. Any questions about this? Yeah?
Wait, so are you saying for P, it shares like Q factors? When you have the P, right, you have kind of Q rows where you have P times, yeah, that one.
Mm-hmm.
Yeah, we have Q rows with each one.
Yes.
Factor P. And for Q, there's a P number of factors for Q.
Yeah, exactly. We are kind of writing them in a grid so that all the factors of p kind of form up in a line, and that happens if we make p columns. If we make p columns, we can just kind of put all the things that have a factor of p in a line and say all of those are no good because they don't have a GCD of 1 with n. In fact, their GCD would be p. That's a problem. So this tells us where all of our factors that have a GCD of p are, and then we can see where all the factors that have a GCD of q are. Yeah?
If like n has more than 2 prime factors,
Yeah.
you cannot use the grid factor. So it's like limited.
This is absolutely limited. I'll tell you in just a moment what the general case is, or I won't tell you what the general case is, but I'll tell you what function it's called. So for now, that's our warm-up. That's just something for us to know. Yeah?
What if P and Q are the same value?
What if P and Q are the same value? I see. As in P squared. N is equal to P squared.
Would it still work?
What's that?
Would it still work? P minus 1, like P minus 1 squared?
I don't believe so. Let's see. I don't believe so. I think you'd get more factors of P than you're actually counting. I could be wrong on that. I would need to remember what's called Euler's totient function. That tells us how to count up the things that have multiplicative inverses. We'll talk about that in a moment, or just reference it. Because, yeah, there's more than we can cover that we want to cover. So for now, this is just kind of a warm-up to get us thinking in the right direction. If we have a product of two primes, we're really asking how many things have multiplicative inverses. Those are the ones that algebra works well. We can cancel. We can do our algebra nicely with multiplication. So I'm going to ask a new question now. And that's, say x is in Zn. Just any integer n. How many times do I have to add it to itself until I get 0 mod n? To some degree, it depends. Like, if x is equal to 0, you don't need to add it to itself at all. It's already 0. But if x is an arbitrary thing, just an arbitrary element of Zn, how many times do I need to add it to itself to get 0 always? Any guesses? Yeah. N times, OK. Yeah, so if we add it n times, that's really x times n, which mod n is always going to be equal to 0. Not too bad, right? We're just trying to see how many times we add it to itself to get 0. New question, how many times do I have to multiply it by itself to get 1 mod n? This one's not so easy, to the degree that I wouldn't expect you to know what the answer is unless you've seen it already. I want black. There we go. That's good. Great. OK. So the question is, really this becomes exponentiation, right? It's asking x to the what is congruent to 1 mod n. And there's no way that you would know this unless you knew it already, because it's not trivial. It has its own little symbol. It's called phi of n. This is Euler's totient function. So do we want this? I think we want that. So where'd my pen go? Yeah, I'll write it right here. Phi of n is equal to the number of, number of multiplicative inverses mod n. It's just kind of a definition. Yeah.
The multiplicative inverse is not the same as like the regular inverse of another number, or am I confused?
Can you say that again?
The multiplicative inverse that we found is not the same as like a regular inverse in like, does that make sense?
What's a regular inverse?
Like let's say like the inverse of 4 mod 6.
That's exactly what we're meaning. We're meaning multiplicative inverse mod a number. So 4 inverse mod 6, what is that? 4 times what is congruent to 1 mod 6? Well, it doesn't, because they share an inverse. I mean, the GCD is not 1. So that's a problem. What is something 5? 5 is something that does have an inverse. In fact, it's going to be 5. 5 times 5 is 25. Mod 6 is 1. So when we're saying multiplicative inverses, we're exactly meaning this type of inverse. Yeah.
The number of multiplicative inverses in what? Just all
Mod n. In Zn.
in the event. Okay.
Yeah.
So it only goes up to whatever n is?
Yes, exactly. Exactly. And basically, we're talking about congruence classes again, like 0 up to n. Why? Because if you go past that, then you jump back into the same congruence classes. Right? And we know that this already is the number of, basically the number of x in Zn such that GCD of x and n is 1. Right? We know that if and only if holds. So if x and n have a greatest common divisor of 1, that means it has a multiplicative inverse and vice versa. So phi of n just counts up how many things have that property. And we won't see phi of n in the general case. It's a little complex. Yeah? I don't think the notes talk about Euler's totient function. The notes don't mention this. The problem is that they're mentioning it subtly in a lot of different ways. So one way to look at this is why even have a function of this? Euler, this is the same Euler from Eulerian Tor. Why do we care about this? You know, he had his finger in a lot of pies. But why do we care about this? Phi of n, the number of multiplicative inverses mod n. It's because when you have the set of things that have multiplicative inverses, it's kind of a group of things that plays really well with multiplication. It's where you can do all your cancellations. It's where you could do all your algebra and have it work out like you expect it to. There are inverses, you can cancel, all that sort of stuff. Yeah, so it's a group of things that works out well with multiplication. In fact, it's part of an area called group theory. We're kind of brushing our toes against something called abstract algebra. And really, this is talking about something called group theory, yeah.
But I didn't really understand what you wrote over there. Are you saying if you multiply x by phi of n, you get 1 mod n?
I'm saying, so yeah, over here, I'm saying the exponent, x to the phi of n, if you multiply x by itself, phi of n times, you get 1. So this is a little abstract, so let's make it a little bit more concrete. What is phi of p for p prime? How many things have multiplicative inverses in Zp? That is the set of 0, 1, 2, all the way up to p minus 1. Any guesses on how many things have multiplicative inverses in Zp? Yeah. We're getting a guess p minus 1. And that's exactly right, because everything has a greatest common divisor of 1 with p, because p is prime. Nothing shares factors with it. Nothing shares factors with p, so the only thing that does is 0, right? So take out 0, everything else is p minus 1. Now, what if we had phi of n, where n is equal to p times q for pq prime? Do we know what that is? Any guesses there?
T minus 1 times Q minus 1?
Yeah. So this is just what we were doing right over here. What we were doing was counting up the things that have multiplicative inverses, mod this sort of thing. N is equal to p times q. So this is where p minus 1 times q minus 1 comes from. You just throw out all the multiples of p and throw out all the multiples of q, except don't forget you threw out 0 twice, so don't do that. But otherwise, phi of n is equal to p minus 1 times q minus 1. So all this is saying is that, I'll give a name for this too. This is a name that I think really, so this is Lagrange's theorem. We won't be proving this. The way this is phrased is group theory. Group theory in abstract algebra really tells us how groups behave, really tells how operations behave. So this is a really powerful thing that really gives a good intuition for why this works. But we don't have time to go into group theory. We hardly have time to go into what we're going into. So we're certainly not going to cover group theory. We just want to see a couple of corollaries of it. One, I don't think we need this anymore. One is called Fermat's little theorem. Right? This is in the notes. This is something that is in the notes. And it is that if you have a prime p, then x to the p minus 1 is congruent to 1 mod p. That's just a special case of Lagrange's theorem, right? P minus 1, that's what phi of p is, right? That's the number of things that are relatively prime to p. So a special case is x to the p minus 1 is congruent to 1. Right? Another special case is if n is equal to p times q for p, such that p and q prime, then, for all x such that the greatest common divisor between x and n is equal to 1, then x to the, in this case, what's phi of n here? It's this. X to the p minus 1 times q minus 1 is congruent to 1 mod p. So we don't have time to go into kind of all the nitty-gritty that we would like to about understanding why these are true. But it is kind of saying something that if you have any number, you can only wrap around the clock so many times before you land on 1. That's what it's saying. How many times can you take x and multiply it by itself? It's going to kind of keep jumping on a new number each time until it finally lands on 1. You can't have too many before it does that. Yeah.
Isn't that mod PQ?
Yes, it is. Thank you. This is mod n. Yeah.
Does this apply to when the prime factorization involves more than 2 primes?
Yes. So if the prime factorization, this has been asked a bit, what if the prime factorization involves more than 2 primes? Then we would need to find out what phi of n is. And there is a closed formula for this, but it's a little bit ugly and doesn't help us too much here. You could look it up on Wikipedia. This is called, I'll just write it out. This is the same Euler as before, Euler's totient. This is Euler's totient function, and it says how many things are relatively prime to n as a function of all of its prime factors. So it kind of breaks it up into all its prime factors. Some of the simplest cases are if you just have a prime or if you just have a product of 2 primes. The reason why we're looking at this is we're going to look at a product of 2 primes today quite a bit. Right? So these are just to have in our back corner as our toolkit. Right, so if you look at the notes do a proof of this. They show Fermat's little theorem. The proof isn't particularly enlightening, but it's clever. So read it. It's good to look at clever proofs sometimes. It just builds our toolkit and mathematical maturity of the amount of things we've seen. But I don't think it shows us too much about why it's true. So Fermat's little theorem is proved in the notes, and then they show how to prove that this also holds from Fermat's little theorem by using Chinese remainder theorem. So it's good to see that. We're not going to see that right now, yeah?
If you don't mind, could you demonstrate that working for something as simple as 9 even?
Oh, sure. You're saying set n to be the product of 2 primes and see that it's true? Yeah, great. So let's set n equal to 3 squared is actually a little trickier. Euler's totient function takes that into account, but it has to do something with that square. So let's look at a product of 2 different primes. So we're going to do, I don't know, 3 times 5 is 15. So those are our 2 primes. And we want to see, can someone give me a number that's relatively prime to 15? Just any number. 7, great. So 7 to the p minus 1 times q minus 1. That's p, that's q. So we have 7 to the 2 times 4. So that's 7 to the 8. And what are we doing this by? We're doing this by mod 15. So let's see. What's the least painful way to do this? What is the least painful way to do this? Well, we can certainly walk through it. So 7 squared is 49. What's that? I feel like people have clever ways to do it, but let's just crunch through it real quick. So 7 squared to the 4, which is 49 to the 4. 49 mod 15 is 4. So that's congruent to 4 to the 4. And 4 squared, we do 4 squared to these 2, which is 16 to the 2. And 16 mod 15, that's 1 already. So 1 squared is 1. So that's just working through an example to seeing that I chose it from the audience. This is a random number, relatively prime to 15. And we showed that when we put it to Euler's totient function, we do, in fact, get 1. Yeah?
So this works for any number between 1 and, I guess, n?
Any number between 1 and n, so long as it's relatively prime to it.
Oh, okay.
Right. If you have 0 and raise it to any power, that's going to stay 0. You're never going to get to 1 if you start with, say, 0. But anything relatively prime to it, anything that has a multiplicative inverse, can't be multiplied by itself too many times before it gets back to 1. All right. So, great. All right. So this is just kind of setting us up with some tools while trying to give us a little bit of intuition. There's this just kind of, we haven't dealt with exponents yet. We just haven't dealt with exponents at all yet. And there's just this neat thing that multiplication, real quick, we've seen this is true for addition, yeah? As in, the same thing is true for addition. How many additive inverses are there mod n? How many additive inverses are there mod n? So I'm hearing n minus 1. So we have the numbers 0, 1, all the way to n minus 1. So we have n numbers here. And for additive inverses, actually every single one of them has an inverse. Right? That's kind of a nice thing about additive inverses. If you're trying to, what's the additive inverse of A? It's just n minus a. Those sum to n, which is 0. So for addition, how many times do you need to add something to itself before it's 0? It's always going to be the number of additive inverses. That's just kind of trivial because there's always all the additive inverses. What's a little weirder is for multiplication, how many times do you need to multiply something by to get 1? It's the number of multiplicative inverses, which isn't always full. In fact, it's whatever phi is. And that's a whole thing you can look up if you're curious. But for now, all we're saying is that we have a toolkit here, and we're going to start using it from here on out. Yeah? Yeah, so the question is why multiplying, why does this true? This is Lagrange's theorem. We're not going to prove it. It is quite deep, honestly. I love this theorem, but it is a special case of something in group theory. It is saying that I don't think there's a way to say it without getting too much into group theory lingo. I would highly recommend checking out group theory, checking out abstract algebra. We're used to algebra in lots of scenarios. We do it over the reals, we do it over the integers, we do algebra all over the place. And now we're doing it over modular arithmetic. But there's even different algebras with different things other than multiplication and addition. There's a whole bunch of different algebras. Abstract algebra abstracts all that and says, actually, they all kind of behave the same, and we can say some general rules about all types of algebra. this is one of the things you can say about all types of algebra, which is, yeah, I can't say it without more lingo, yeah.
Even for the additive inverses, why does, like, if you're saying like n is a number such that adding x n times will be equal to 0 mod n, why does that mean n is the number of additive inverses?
The number of additive inverses isn't because of this. The number of additive inverses, we can just check. Choose any a that you want in Zn. There will be an additive inverse, namely n minus a. When you add those together, you get n, which is the same thing as 0 mod n. So I'm just saying that the number of additive inverses is always n, just by construction. Addition works real nicely. Multiplication is not as nice. But it does have structure. We don't have enough machinery and tools as far as abstract algebra goes to really prove why this is true in general. Yeah, we can't see why that's true in general right now. But we are going to use it. This one is showed in the notes, Fermat's little theorem. This one, I don't know if it's showed in the notes. Or no, it is showed through the notes by showing that Fermat's little theorem can show this. It is a more general thing. And we don't get to see why it's more general. But so long as you have Euler's totient function, you can break up n into however many products of primes you want. I'm going to erase this. The reason why we did this was just to see that Euler's totient function is p minus 1 times q minus 1 when n is a product of two primes. That is, there's exactly this many of things that have multiplicative inverses. All right, so I'm going to go over here. So we're going to play a little game now. I once again have a number in my head that I'm not telling you. I have x. And I could have you guess x, but in this time, x is actually kind of small. You might actually be able to guess it. So I won't try to have you guess it, but I do have it written in here. So I have a number written in here that I can show you. It's big. So I'm not telling you what it is, but I'll give you a hint. And the hint is that x to the 7 is congruent to 3 mod 11. And I want you to tell me what my number is. So this one isn't so clear. This could be hard. Maybe some of you might be able to do it. But we haven't dealt with this before. We've been able to do multiplication. You know, we've solved a lot of algebra problems in modular arithmetic. We've never dealt with exponents or how to deal with them yet. So how do we get rid of that 7? If this was in the reals, right? If this was in R, the reals, if I had x to the 7th is equal to 1/3, not 1/3, what am I saying? Is equal to 3, what I would do is I'd take the 7th root of it. I'd exponentiate it to the 1/7, right? That's all I would do if I was in the reals. But we're not in the reals. Where'd my paper go? Right? What this gives us is that the reason why we do this is because x to the 7 times 1/7 is equal to x to the 1, right? Like that's what gives us something nice. So in this case, we're not even really caring about what x is, right? We don't even really care about what x is. All we care about is what's happening up in the exponents, like up in the exponent land up there. Right? But we can't do that here. What does it mean? What does x to the 1/7 mean if we're in modular arithmetic? What does that possibly mean? Because what I want to do is turn my phone off. What I want to do is I want x to the 7 times some d so that when I look at it, it becomes x to the 1. Mod 11 in this case. Right? If I was able to do that, if I was able to kind of get rid of the 7 up there, then I could just raise both sides to the d, and I'd get x is congruent to 3 to the whatever d is. So we're dealing with exponents for the first time. How do we do this? Right? That's the question. And we don't really know how to do this yet. But what do we know? We've learned just a few things a moment ago. Yeah?
Wait, how did you go from like 3 to x to the 1?
3 on the left side. 3 to x to the 1. This is what we want. I'm saying what we would like is we'd like a d so that if we raised it to, so that we could do 7 to the d, because if that was the case, we could do x to the 7 to the d is congruent to 3 to the d. And if x to the 7 to the d was equal to 1, then we could just do x is equal to 3 to the d, and we'd be done. Right? So we're trying to find a d that kind of cancels out the 7. We know how to cancel when we're multiplying, but we've never dealt with exponents before. So we're trying to understand what does it mean to cancel exponents? How can we cancel exponents? This is the new thing. OK. So what do we know so far? Not too much. Yeah? 7 and 11 are relatively prime. That helps us. And what we also know is we don't know too much, but we do know something special. Because 11 is prime, we know that x to the 11 minus 1 is going to be congruent to 1 mod 11. Why? Well, that's just what Fermat's little theorem tells us. Right? This is the tool we have so far. We can raise something to p minus 1 power and have it be congruent to 1 if we're dealing with a prime. And we're dealing with a prime. So this is what we have in our toolkit so far. Yeah?
How do you know that x is prime?
We don't know x is prime, but we do know 11 is prime. Right. Yeah. So we don't know anything about x yet. That's in my head. It's in my folder, actually. I'm trying to. That's what we're trying to figure out. But we do know 11 is prime, so we know that this property holds. This is Fermat's little theorem. I'll even write FLT here. Fermat's little theorem. Right. What does that tell us? It tells us, well, x to the 10 is 1. I'll just write this out a little bit more. X to the 11 minus 1 is equal to x to the 10. So if what we're trying to get is something like this, we know that x to the 11 is congruent to x mod 11. Right. I just multiplied by x on both sides. And now we feel like we're close. Because now if I could 7 times something is equal to 11, we'd be great. But 11's prime. 7 times something will never equal 11. So we're not so great yet. But what else will make this true? This isn't so obvious. But x to the what else will be congruent to x mod 11? Any guesses there? Yeah. Right. We have 21 here. Why does 21 work? Well, let's write it out. X to the 21 is going to be equal to x times 10 times 2 plus 1. That's going to be equal to x to the 10 to the 2 times x. And x to the 10, that's 1. So that's going to be congruent to x mod 11. This is more general too. What's another thing that this would be true for other than 11 and 21? Any other guesses? 31, exactly. So this will be true for x to the 31. It'll also be true for x to the 41 and 51 and so on. Yeah, so it's kind of this weird thing where we're dealing with modulus 11, but we want something to be true about the exponents, which is a whole different thing. We want something to be true about the exponents, and what we can say, let's see, where do I want to write this? We'll write it here. What we want is that 7 times d will be congruent to 1 mod 10. I'll remove this a little bit. So this is weird. Where did this come from? The problem we have is that we're dealing mod 11, so why are we moving to mod 10? It's because we're not working anymore in the land of x's and y. Yeah? Sure. Yeah. So 21, that's going to be x to the 10 times 2 plus 1. And x to the 10, this is where we can use Fermat's little theorem to say that's just 1. Right. So really, x to the 10 times anything plus 1, that will be equal to x to the 10 to the k times x, which will always be congruent to x mod 11. So it's this kind of weird thing where even though we're dealing with mod 11 and we're doing multiplications here, what we care about right now is canceling in the exponent, which puts us into a whole different modulus. Now we're dealing in this kind of like this exponent land. And now that we're in exponent land, we're dealing with solving a different equation. That is, we want 7 times d to be congruent to 1 mod 10. Let's expand that out, because that seems like it comes out of nowhere a little bit. What does this say? It means that 7d is some multiple of 10 with a remainder of 1. Right. What we want is that 7 and d cancels to 1, but we're not working mod 11 because, again, that's not where our domain is. We're up here in the clouds with the exponents. We want 7 to d to cancel somewhere else, not with mod 11. So, you know, let's... Right. So we want something with a remainder. We can solve for this. You know, if we already have 21, and we know we're looking for 7 times something that will get us back to x. So we already know that d is equal to 3. Right. Kind of a weird thing, but we can solve it here. If we're not convinced that d equals to 3, well, what does 7 times d equal 1 mean, mod 10? That means that 7 inverse, well, d is equal to 7 inverse, mod 10. Yeah? Yeah. Yeah. How did we get to mod 10? The way we got to mod 10 is this is the 10 that's important. Here's our p minus 1, our 11 minus 1, 10. That's the thing that kind of cancels out to 1 here. Right. So when we got to here, we had 11. X to the 11 is congruent to x. 31 works. 21, 31, 41, all these things. I think I need more room, so let's make more room. Yeah, please.
The mod 10. Where are we at? 70. Where's the 70 that was on the board? Yeah.
70, yeah.
You want this thing to be 1 more than a multiple of 10. Because if it was a multiple, so if it's 1 more than a multiple of 10, then after you, I don't know, never mind. But the goal is you want this 70 to be 1 more than a multiple of 10. That's the goal. Then you're left with just x after you mod. Yeah.
So, so because we have x to the 10 is congruent to x, congruent to 1, we're just going to kind of rewrite what we wrote over there to kind of make more sense of it. We have x to the 11 is congruent to x. And what we're trying to do, again, is x to the 7 times d. We want a d that cancels out the 7 so that we just have 1 in the exponent. How do we do that? Well, we don't have a d that when we multiply by 7 gets us 11. But the reason this works is because it's x to the 10 times x. And x to the 10 is just 1. We can do x to the 10 times x to the 10 times x. That's still the same thing as x. These are all equal to x. Because this just becomes 1. This just becomes 1. I could add another x to the 10 there. I could add another x to the 10 there. You can add as many x to the 10s as you want. And what you're left with is a remainder of 1 there to get x. So x to the 41, x to the 41 is the same as x to the 31 is the same as x to the 51, x to the 21, And those are all congruent to x when we're dealing with mod 11. So where does the 10 come from? It comes from this. Here's our multiples of 10. And they just kind of all wipe away when we're dealing with Fermat's little theorem. The 10 comes from Fermat's little theorem, right? This is where we kind of get our cancellation to just be 1. So there's this weird kind of like change of hands here where we're dealing with mod 11, but if we're dealing in the exponent world, so like the main point I want to make is, yeah, we're kind of trying to think mod 11, but really if we're thinking in the exponent land, the top ones up here, here's x to the 1. Now we're dealing mod 10. So this is the weird thing. It's hard to think about exponents in modular arithmetic. It is a new kind of thing that we haven't done yet. We're really kind of thinking in the exponent land and saying, what's the relevant modulus there? Because of Fermat's little theorem, the relevant modulus turns out to be 10. Weird. So let's see. Let's just kind of finish this and kind of see if we make sense of it. So yeah, let's solve it. So we want this to be true. X times 7 to the d, 7 times d is congruent to that. So really what I want is I want 7 times d. That's going to be, again, in the exponent land. I'd really like that to end up being 10 times k plus 1 somehow. Does that make sense? If I get 10k plus 1 up there, I can rewrite it as x to the 10 to the k times x, and then that goes away to just be 1. Hearing some eurekas, that's great. It is weird. It is a conceptual jump to jump from the ground to the clouds where exponents are living and come up with a new modulus. But what we're really looking for is 7 times d is congruent to 10k plus 1. And one way to say that 7d is actually equal to 10k plus 1, is that 7 times d is congruent to 1. Let's lose all this. Mod 10, that's what we're dealing with. We're in exponent land. And what does that mean? That means we're looking for d being equal to 7 inverse mod 10. Right? This is just saying d is the thing you multiply 7 by to get 1. That's the definition of multiplicative inverse. So what is the multiplicative inverse of 7 mod 10? Yeah, 3. 3 is d equals 3 because 3 times 7 is 21. Mod 10 is 1. So let's go ahead and kind of plug everything back in and then celebrate. So we found d equals 3. And so if we plug that in, we get x to the 7 times 3, which is x to the 21, which is really x to the 10 times 2 times x. I just broke off that 10 because really that's the thing that cancels away to 1. That's Fermat's theorem. And now we're left with x. And the real point is we do that on both sides. So 3 to the 3, right? If I raise both of these to 3, this is how we're solving the equation. We're trying to get rid of that 7 in the exponent. If we raise both of these to the power of 3, what I get is x to the 21. X to the 10 cancels. All we're left with is x, and that's equal to 3 to the 3, which is 27. Mod 11 is, what's that mod 11? 5? Great. Great. And let's 5, right? So that's the number, right? I didn't want you to guess that because it's small enough that some of y'all might have guessed it. But what we did is a pretty powerful thing, right? 5 isn't an impressive number. But what we did is we found a way to cancel exponents. And it's weird because we have to kind of jump up a level into exponent land and deal with a different modulus. But that's a very crucial concept. I don't think we'll get to all the things we want to get to today. We have time, so we're going to do more. But this concept is very crucial, that we're able to cancel exponents, even in modular arithmetic land. All right. So also, we just played a game. And I'm going to write out what that game is, because it's an important one. Here's the game we played. You're given x to the e. You're given the exponent e. And you're giving p a prime. And your job is to find out what x is. Basically, taking the eth root of something, except in modular arithmetic land. That's the goal. And it turns out this game is actually kind of easy. It's hard because we have to learn what taking an exponent means. But like algorithmically, you'd be able to program this without too much ado. And the way it works is exactly what we did. We find d such that, so we're going to kind of congeal all our thoughts here. We had to think quite a bit there, and now we're going to congeal our thoughts. Find d such that, what's the game here? Yeah, right. Such that e times d is congruent to 1 mod p minus 1. This is where we're changing, oh, I missed something. We're given x to the e mod p. Sorry. So we're given x to the e mod p, e, and a p that's a prime. I'm going to rewrite this a little bit, np. And what we're doing is we're trying to find we're trying to find a d that is the multiplicative inverse of e mod 1. Here's where the change of hats goes, right? We were working with mod p. Now we're working mod p minus 1. This is where the modulus changes because we're no longer working in the original modular arithmetic we're dealing with. We're working in exponent land, up in the clouds. And why does this work? This is where we're going to kind of congeal our thoughts. X to the e to the d. Again, if we were in reals, we would just do 1 over e, and that would make sense. X to the e to the 1 over e, those cancel. We're happy. We can't do that. So we need to find some d. And what does it mean for e? Ed is a multiple of p minus 1 with a remainder of 1. So let's, x to the ed is the same as x to the p minus 1 k plus 1. That's what it means for ed to be congruent to 1 mod p. That is, it's a multiple of p minus 1 except with a remainder of 1. And what we can do there is just group. X to the p minus 1 to the k times x. This goes away to 1. And what we're left with is x. This is getting small here, but this is actually, rather than doing that, we're going to do p So this is the game, and it's an easy game in that you can find D pretty easily. You're just finding an inverse. All right. What's our time looking like? We want to see how much we want to get into of this. OK. So I think we'll introduce cryptography and then talk about RSA next class. Right. RSA is a type of encryption algorithm. It plays a pretty similar game to this, except it's not easy. And we're going to see why it's not easy. But the real important point that we want to take away from today's lesson is how to cancel exponents. Right. And that's, again, this little change of hats where you jump to a different modulus. All right. So I'm going to erase all of this. Does anyone want this? Yeah.
I have a question. If you're not constrained by Z of P, then you can have multiple values for D. They don't have to.
Sorry, can you say that again? If we're not constrained by...
Constrained within the ZP space, then we can have
I see. Yes, that sounds right. Yeah, if we're going past P minus 1 into, like, right, higher numbers. Sure. Was there a hand there? Yeah.
So X and E should all be integers?
Yes, X and E are all integers. What's that?
X and E and D.
Yes, exactly. What does it mean to take X to the 1/3 if we're in mod 7? You know, like we'd have to define that. And the way I would start defining that would be with all of this stuff, honestly. Like if we wanted to define it, we'd probably start defining it mod 6. Like it'd be weird because we're doing mod 7, but the exponents are kind of looking mod 6. We'd have to start defining what 1/3 means that way. Right now, we don't have a definition of 1/3 unless we start thinking of our definition in this sort of way where like you jump into a different modulus class up in the exponents. OK. Can I erase this? Great. All right. So we just have time to introduce what cryptography is, and then we'll give an actual scheme next time. I did want to spend a little bit of time at the beginning talking about Chinese remainder theorem, because it's on your homework. And hopefully that's helpful. But yeah, so let's talk about what cryptography is. And this is one of those places where, once again, we're jumping from math land to the real world. And I do just kind of want to put a signpost there that, like, we've been doing a lot of things dealing with truth and proofs and all this sort of stuff. When we jump into cryptography, we're jumping into a very human construct, something that's not fundamentally true or not. It is an invention that we are creating. And yeah, there's a whole bunch of things to say on it. It has a whole bunch of history, too. Cryptography has some of the most interesting history. And again, we're jumping into the real world, which has a whole different baggage of what we might want to say about things. Phil Rogaway has this great paper called The Moral Character of Cryptographic Work. Again, the moral character of cryptographic work, it's a whole thing of like, what is cryptography doing in the world, and when can we use it for different reasons? So now that we're in the real world, I would suggest reading things like that. They're quite good to read. But what is encryption? We always kind of think of it, or there's a lot of things about cryptography, too. There's cryptocurrency, there's smart contracts, there's zero-knowledge stuff, there's bit commitment schemes, encryption. What we're going to look at is just sending messages back and forth. We have Alice and Bob. These are kind of the canonical figures in cryptography. And they're always trying to communicate to each other, while some person named Eve, is eavesdropping. They are listening to the messages going back and forth, and they're trying to learn what conversation is happening. So what it means, you know, what Alice wants to do is send a message X to Bob, but Eve's right here listening, and that's a problem. If you send that message X, Eve now knows what it is. So the idea is Alice and Bob both hold a secret key. They both know it. No one else knows it. It's their own secret key. And they want to encrypt X with that secret key and send that instead. So Bob gets Y instead of X. It's an encryption of X. And then to decrypt it, Bob takes X and runs a decryption algorithm on Y using the same secret key. So we haven't said much yet. This is just kind of the outline of what's happening. We want kind of two things from this. What we want is that encryption and decryption are easy. That is, they're easy to compute. They're easy to compute if you have the secret S with S. And the thing is, the other thing we want is that if you look at the encryption, it looks like nonsense. It looks nonsense without S. So it's kind of two things. We wanted Alice and Bob to have an easy time sending messages back and forth. So long as they have the secret key, they can encrypt and decrypt easily. But anyone else looking at it, another way to say this is X is hard to recover without S. Hard to recover, let's say it out a little bit more, from Y without S. And there's a whole bunch of different notions of security. There's stronger notions, there's weaker notions, there's all these different types of notions of what it means to be secure. But at its highest level, we just have three kind of players in this game where Alice is sending a message that's encrypted, Bob can decrypt it, and Eve can't learn anything if she doesn't have the secret key. Yeah?
Is that saying that the encryption of S looks like nonsense without decrypting using S, or
Yeah.
doesn't contain, is that, it also doesn't contain?
No. This is saying if you don't have the secret key S, looking at the encryption looks like random bits. It looks completely like garbage. You really can't tell it heads from tails from it unless you have the secret key and can decrypt it as well. Right. So, yeah. We have 2 minutes. That means we can't really get to anything else. I could show you a cool thing, or we could end there. Cool thing? OK, let's show a cool thing. I never have time to do this because I never have time. We're always chasing the curricula. So I'll just show you how weird numbers can get. I'll just choose a random number. Can someone pull out a calculator and tell me what this is? So let's choose a number. Let's say 142,857. And show me on your fingers what you want me to multiply this by. I'm seeing 4 there. Sure, 4. Can someone tell me what this is when I multiply these two? 571,428. Nothing too interesting about that, right? I take 142,857 and multiply by 4 and get 571,428. OK, so I'm hearing some laughter. What's weird about this? Yeah, OK, I'm hearing some woes. So this just kind of rearranged the digits. 142,857 times 4 just rearranged the digits. That doesn't usually happen when I multiply numbers. So what's going on here? 857. I can multiply this by, I don't know, let's say 5. Well, I know 5's here. If someone with a calculator wants to tell me, 714,285. OK. Another weird thing. Let's see. What did we do? We just took 7 and kind of put it to the front. So 714,285 is the same as that. 2857. Let's multiply it by 3. What do I get there? I get a 1. If you had a guess what happened, I might guess this is 428571. Someone with a calculator, is that right? That's right. OK, that's weird. So we can keep doing that. We can see that it's kind of true for everything. 142,857. I can even multiply by 7. I get what there? A 9. Ooh. A 9 doesn't work. What happens if I have a 9 there? Yeah. Numbers are weird. Numbers are real weird. Like, we're playing in number theory, but we don't get to play with it because we're moving so fast. If you really look at numbers, all sorts of weird things happen, and it's right under your nose. Multiplication we've known forever, but things get real strange.